Hello everyone, I am Colin Kurz, and this is my report for Lab 2, Motion of a Falling Object. The purpose of this lab was to analyze the motion of a falling object. To accomplish this, a video of an object falling was taken and compared to two different computational models of that object falling, one that included only the force of gravity and one that included the forces of gravity and drag. The result was that the latter computational model was much more accurate in describing the position of the object over time than the former. The fundamental physics principle of this lab was Newton's second law of motion, which states that the net force acting on a moving object is the product of the object's mass and acceleration. Derived from this law are the velocity update and position update equations, which were also used in this lab. Also important is the concept that net force is equal to all of the forces acting on a system added up. In the instance of this lab, there are two forces acting upon the motion of the object, gravity and drag. These two forces are highly important because they act upon pretty much every moving object on Earth. The acceleration due to gravity is negative 9.8 meters per second squared, and the force of drag in this case is equal to a constant times the square of the speed of the object, acting against the object's motion, in this case, acting in an upwards direction. For this lab, the choice of object to take a video of and analyze was a paper ball. A pen with a ruler engraved in it was used as a calibration stick. In Tracker, the y-axis was aligned with the trajectory of the paper ball in order to ensure that any change in the x direction was minimal. This was needed so that the speed of the ball was relatively equal to its velocity in the y direction, thus eliminating a potential error that the velocity in the y direction and the speed were not equal. In the scope of this lab, the system was the paper ball and the surroundings were the air it was falling through. The importance and impact of the surroundings on the system will be shown later. The gravity-only prediction of the motion of the object was created by using the force of gravity to update the velocity and position every 0.001 second. Calculating the force of gravity involved just multiplying the mass of the ball by the acceleration due to gravity by the unit vector in the y direction, as seen in the coding. The rest of the coding involved just updating the ball's position and velocity over time using the appropriate equations. Initial velocity was 0 because the ball started at a state of rest. The resulting predictive graphs of y position over time and velocity over time are shown. Notice that the velocity graph is linear. The gravity and drag prediction of the motion of the object was created by using net force to update the velocity and position every 0.001 seconds. Calculating net force involved adding the force of gravity calculation used previously to the drag force equal to a constant b times the square of the magnitude of the ball's velocity. In this case, b was equal to 0.00744. Again, initial velocity was 0. The rest of the coding involved just updating the ball's position and velocity over time using the appropriate equations. The resulting predictive graphs of y position over time and velocity over time are shown. Notice that the velocity graph is curved. The result of graphing the motion of the real object along with the predictive graphs was that the model of the motion of the object accounting for drag was much more accurate to the motion of the real object than the model that did not account for drag. This is visible in how the model not accounting for drag predicts the y position to dip far below where the other two models do. This is also observable in the difference between the velocity graphs of the two models discussed earlier. The reason for these differences is simple. Drag is a force that acts on all moving objects here on Earth, so to leave it out would be to leave out a crucial part of the net force acting on the object. As shown by Newton's second law, net force is absolutely critical to the motion of an object, so it must be calculated accurately. Some remaining questions are, which model predicts a terminal velocity? Terminal velocity occurs when the force of drag pointing up equals the force of gravity pointing down. This essentially means that the net force will become 0, causing a velocity to become constant. The model that predicts this is the one accounting for drag, for its velocity graph becomes shallower over time and approaches a single constant value. This is in contrast to the model not accounting for drag, which has a constantly decreasing velocity. Would the terminal velocity change if the object was thrown downwards? The answer is no. Drag force is a function of solely velocity, so the velocity at which the drag force would equal the force of gravity would remain the same. It would just occur at an earlier time because of the initial velocity boost. This is seen in how the original velocity graph and the velocity graph with the object thrown downwards start different but converge towards a single terminal velocity. In summary, it is absolutely critical to account for all forces acting upon an object when predicting its motion. Leaving any force out can lead to inaccuracy in results, for Newton's second law means that an accurate net force is needed to predict motion.